everybody. Okay, we are going to move on with our intramolecular bonding today, and we're going to wrap up with the third of three categories of bonds. So we'll talk a little bit about metallic bonding. That won't take me long. And then we're going to move on from here to talk about overall molecule shape. So let's see where we will begin. And here we are. It is April 2nd. We'll start with some metallic bond characteristics. So metallic bonds are very strong intramolecular bonds. And because they're so strong, there's high melting and boiling points for metals. And by the way, as a reminder, table S has the melting and boiling points of all elements, okay, including the metals, okay. The shape of metallic bonds are what we would call a crystalline lattice. It looks similar to that sodium chloride shape, but with only one type of element. And I showed you the sodium chloride shape in the previous video. A key thing to relate to metallic bonds is the following. There is a sea of mobile electrons flowing around the kernel of the atoms. And this imparts important characteristics, heat or thermal and electrical conductivity. Here's a way to visualize metallic bonding. Okay, a few more characteristics of metallic bonds. They are malleable. So like in this spoon, we can shape metals into a wide variety of options. They are ductile. They can be made or drawn out into wire. And as shown again with this shiny spoon, they have luster, a lot of metals. And the way we can represent those metals and their metallic bonding is very simple, like copper in the solid form, aluminum, magnesium, and many other examples. So that concludes metallic bonding. Nice and quick and simple. All right, we're going to go on and talk a little bit about shapes of molecules. Okay, there are 5 main shapes of molecules you need to be familiar with, and I will demonstrate them for you now. The first shape is linear shape, and I actually have mentioned this several times over the course of the lessons, and I'm kind of looking here at all my options, and I've got a lot of options here. These are all examples of linear shaped molecules, okay? They could have some double bonds involved, but they're straight line. This has a triple bond involved, another double, and these have all single bonds. They are linear in overall shape. Well, then we have planar triangle, and we haven't really talked about that one much yet. And there's not a lot of examples out there. And my model kit only allows me to do one example for you because this model kit, the colors represent certain elements, and I don't want to be interchanging the wrong colors just to make it right. But this is a good example of a planar triangle molecule. Think planar, think the Great Plains. It's very flat, okay, on one angle. But when you are looking at the bird's eye view, you have a triangle shape. So this is a planar triangle molecule. And this happens to be formaldehyde, by the way, a pretty nasty chemical. Okay, the next one, the bent shape. I hope you're thinking water right off the bat. And we have mentioned that several times. Water is a good example of a bent shape molecule. Pyramidal, this one's a new one. Okay, as you're looking down, a bird's eye view, okay, you're going to see kind of this, it looks triangular, or sometimes we call it trigonal pyramidal. Okay, the key is this element here, which happens to be nitrogen, by the way, and these are 3 hydrogens, so this is ammonia. This nitrogen is elevated above, so hopefully you'll be able to see that there. So it's got like a pyramid shape, okay? And the 5th shape that you need to be familiar with, I've got 2 examples of them here. And these are tetrahedral, tetra, 4, okay? One thing I want you to notice with these, every angle between all of these atoms bonded is the same size angle, okay? And this makes the tetrahedral shape. Now, the difference between these 2 is just one element. This happens to be bromomethane, and I'm going to talk more in detail about this example in a few minutes, okay? This happens to be plain old methane, okay? And you had to do some bonding with this example. All right, so let's see what we have here. Okay. The next thing I want to talk about with just one example, and you're going to see others in an assignment you're going to get, but I want to be really clear about the difference between bond polarity and molecular polarity. So it's been a few weeks now that we've been talking about polarity. Now I'm going to really get a little more detailed here. When we talk about bond polarity, we're talking about intramolecular bonds and whether this bond here is polar or not. Whereas when we talk about molecular polarity, we're talking about this overall molecule. And this, as I mentioned, is bromomethane, and here's my little ball and stick model of that. So polarity is described in both ways, at the intramolecular level and at the overall molecular level. Okay, so in using this example of bromomethane, what you need to do is look on table S, as in the past. Use a marker here, and bromine is represented here by this orange sphere. And when I look up on table S, I see that the electronegativity of bromine is 3. When I look up carbon on table S, I see that it has an electronegativity of 2.6. So when I want to assess whether this bond is polar or not, 3.0 minus 2.6, 0.4, it's actually non-polar covalent. Now, just as a quick reminder, this is going to go back to a few lessons ago. Non-polar covalent bonds are going to range from 0 to about 0.5 electronegativity difference. So since this is 0.4, this is non-polar covalent as a bond. All right, and that's between bromine and carbon. Now we have 3 other bonds, and that are between carbon and hydrogen. And when I look up hydrogen in table S, it has an electronegativity of 2.2. So 2.6 minus 2.2 gives us a 0.4 difference. This is also non-polar covalent. So actually all 4 bonds, they're all 4 single bonds, and they are all non-polar covalent. Now, let's look at molecular polarity with this particular example. Overall, let me use a different color. I'll go red here. Okay, overall, you're going to have a greater attraction for these electrons by bromine, right? So I'm just going to kind of draw a little arrow there. Bromine has a 3.0 attraction for the electrons in this bond. Now, carbon has a greater attraction than all the hydrogens and is going to be pulling these electrons a little more closely to it. So overall, this molecule actually has a slightly polar end, slightly negative end here, and therefore the molecule is polar, even though all of the individual bonds are nonpolar. Okay, so this is a really good example, and you will see a few more. You'll have a reading to do and some other problems to do regarding this. All right. Looking at another example, though, going back to that methane, you will note that all four elements surrounding the carbon are identical. They're all hydrogen. They're all going to have the same electron negativity difference, 0.4. And in this case, that carbon is kind of pulling the electrons a little bit closer to itself. But again, because these angles are identical and these are all the same type of element here, this molecule is not only going to have nonpolar covalent bonds, but overall, this molecule is nonpolar. Have a great day. Bye.